In number 8, we're looking at the population of a certain country every 10 years. And here's our data that we're going to want to open in StatCrunch. Well, we just want to see that if as time passes, the population is growing at a predictable linear rate. So we're going to go to regression, simple linear, and we're going to see if the year can help predict what the population will be. So let's compute that, and you get the regression equation right up here at the top. And that's what we want for part A, the least squared regression equation, with our year as our explanatory variable x. And so now we're going to test whether a linear relationship exists using a hypothesis test on the slope. So our null is always that the slope is going to be 0, and our alternative is that it's not 0, that the slope's either positive or negative, but that there is some slope to the regression equation. So the p-value of that, jumping back into StatCrunch, you'd go to slope and go all the way over and get the p-value, and that is way below alpha. And so we will reject the null hypothesis, which was that there's no slope, and accept the alternative. So there is sufficient evidence to conclude that a linear relation exists between the year and the population. So going forward, we're going to see what a scatter diagram would look like of our data. So coming back in here, you would go to graph, scatter plot, and our years are X, our populations are Y. Hit compute, and you have that nice looking like a linear upward trend here. And so match that to the correct graph. Then for D, we want to actually look at the residuals. So that's measuring how far off the actual Y values of the data are from these predicted values we're getting back with this equation. So to do that, we want to go to stat, regression, simple linear, and if you scroll down, you'll have the option to do the residual plot as a graph. So go ahead and compute that, and you'll have to click over here at the bottom to move away from the numbers to get the actual graph. And you'll see the residual plot looks like this. And this is one of the things that we want to watch out for with the residual plot is a pattern, a shape, and we have a pretty clear U shape here where we're above with the residual, then it dips below, and then it's coming back up. And so match that to the correct shape, and the conclusion from that is that a linear model is not going to be appropriate based off of this residual plot. And to conclude number 8 here, the moral, or kind of just summing up everything we just did, is that inferential procedures may indicate that a linear relation between the two variables exists. And that's just saying that our hypothesis test, that the result of that was that a linear relationship existed. Looking at the scatter diagram, it seemed like a linear relation existed, but diagnostic tools such as this residual plot we just did indicate that a linear model is inappropriate for this data. For number 9, the two variables we're looking at is our explanatory variable, how much the CEO is compensated, and then the response variable is how well the company's stock price is doing. So if we want to open that in StatCrunch and first start looking at getting the values that would go in our residual equation, we want the compensation to predict the return on those stock prices. So here we get the values that would go in the residual line. The B1 is the slope, and B0 is that y-intercept there. And then we're going to do a hypothesis test. And in a hypothesis test, we're looking at the slope. We're always assuming our null is that there's no slope. And the alternative we're trying to see is if there is a slope different from 0. And it actually wants us to show the test statistic here. So again, making sure you're in that row for slope. enter in what the test statistic is based off of our sample data. And then the p-value is shown right there as well next to the test statistic. You'll enter that as well. And that is higher than our alpha. And anytime we get a p-value that's larger than alpha, we do not reject the null hypothesis. So in this case, it means that there is not sufficient evidence to conclude that a linear relation exists between the compensation of the CEO and the company's stock return. So we're going to kind of do that same test here with a confidence interval in part C. So if you go back and edit this simple linear regression, and instead of picking hypothesis test, do confidence intervals. Make sure you have the right level of confidence and hit compute. And looking at slope again, you can scroll over and you'll see the lower and upper limits of our confidence interval. And so since the lower limit's negative and the upper limit's positive, that means 0 is in that confidence interval, which once again indicates there's not enough evidence to discard our null hypothesis that there is no slope of this regression line. And then finally, just kind of conclude what that confidence interval and hypothesis test, what conclusion would that make us reach? And so based on those results, the regression line should not be used to predict the stock return. It would not be a good idea to plug in salaries for CEOs and try to use that to predict how a company's stock would perform. And so since we don't have a regression equation, what you want to use instead is just the mean stock return from our sample data. Number 10 here, very similar to number 8. We're looking at the population of a country as it's changing over time and seeing if that change in time can be used to predict then what the population will be. So first find the least squared regression equation, stat, regression, simple linear. Can the year be used to predict the population? You hit compute and you get the least squared regression equation up there at the top. And then to test the slope here to see if it's a good idea to use the least squares regression, our hypothesis test is always the slope will be 0, and the alternative is then that the slope is not equal to 0. So to find the p-value of that, you go to the slope here in the chart and scroll over and it shows you the p-value. Now since this p-value is below alpha, we will reject the null hypothesis and assume the alternative is true, which just the conclusion of that is that there is sufficient evidence to conclude that a linear relation exists between year and population, because we're accepting the alternative here that the slope of the regression equation is not equal to 0. It's either positive or negative. So drawing a scatter diagram, we do that by going to graph, scatter plot, pick your X and your Y, and you hit compute and you see what it'll look like. So select that as well. So all the evidence is pointing towards it is a good idea to use this linear regression equation. It seems that there is a linear relationship between these two variables, everything we've looked at so far. But we need to actually dig deeper and make sure that a linear model is actually appropriate. And the way we can do that is by looking at the residuals. And StatCrunch will calculate those for us. So going back into regression, simple linear, we need to scroll down to where it says a residual index plot. We want that graph. So hit compute on that. And when we scroll over to look at that residual plot, we see this distinctive pattern here, a U shape. And when something like that occurs in a residual plot, it means a linear model is not appropriate. So no, a linear model does not seem appropriate. And what we learned from all that is the moral is that inferential procedures, what we did earlier here with the hypothesis test, drawing the scatter plot, may indicate that a linear relation between the variables exists, even though the diagnostic tools, like the residual plot, indicate that a linear model is inappropriate. So we can't just rely on these inferential procedures. We need to always make sure we're doing the diagnostic tools as well before we jump to the conclusion that a linear model is appropriate.